Well, thank you very much to the Studium for this invitation to talk to you today. Hang on to your chairs because I'm going to take you on a voyage in time and in space. Well, not exactly space, but you have to put your minds back nearly 4 billion years ago. I'm going to talk to you about the Earth, an Earth that's completely different to the Earth today, about a time when the only inhabitants of the Earth were microbes, and these are our ancestors. Okay, we were talking a little bit about the Vikings in Normandy. Now we're going back a little bit further in time. So, first of all, thank you very much to the Studium, and also to Paul Vini, because I've been here in Orléans since 2002 at the Centre de Biophysique Moléculaire, and I'm here at the invitation of André Braque, my predecessor. Let me see if I can get this working. Yes, André Braque, my predecessor, who founded the exobiology group with prebiotic chemistry, and also Paul Vini. So thank you, Paul. And this is a photograph of me, hot and bothered. I'm in the mountains in South Africa collecting the rocks, and I'll show you the fossils that are in these rocks. So, first of all, a little bit about our group. What is exobiology? What is astrobiology? Frankly, it's the story of everything, because it's the story of the origin of life, it's the story of where we came from, it's the story of how the planets formed, how habitable conditions formed, it's the story about how life survives in extreme environments on other planets, it's the story about the future of life, and it's also the story about all the philosophical aspects, the sociological aspects of life. If we find traces of life on Mars, what is the general public going to think? Most of the time they think, oh no, we're going to bring samples back from Mars and we're going to contaminate the Earth. Well, anyway. So, our group because of all of this, our group is a very, very diversified group. There are physicists, geologists, geobiologists, microbiologists, biochemists, space engineers, prebiotic chemists, etc. And we need all of this to understand the origin of life, where life came from, and everything that we're doing. And in fact, quite a few of our group are Studium Fellows. So we're very thankful to the Studium also for the support for our group. Now, I'm going to talk to you about a number of things, except for one thing. This probably interests you, but I won't have the time to tell you about it. Why on earth are we interested in the oldest traces of life on Earth? What are the constraints looking for the oldest traces of life on Earth? I'm going to set the scene. I'm going to tell you something about the environment of the early Earth, because it was a totally different planet. I'm going to show you what we actually find and talk about the difficulties. And then I'm going to talk about all of this, how all of this helps us search for life elsewhere, and in particular on Mars. So this is one of my favorite views of our planet Earth from space. It shows the Earth today. The Earth today is populated everywhere. There's life everywhere, in the seas, in the skies, on land, a huge variety of life. We even have some technologically capable apes. Quite technologically capable, but I'm not too sure about the intelligence. But on the early Earth, go back 3 to 4 billion years ago, all we have are microbes. And these photographs here are photographs of microbes that lived 3.5 billion years ago, 3,500 million years ago. These are photographs that I took from rocks that came from Australia. I took the photographs 2,000 years ago. I'm still fighting with certain people who don't even believe that these are fossil microbes, and this is on Earth with all the technology that I'm throwing at it, and I'll show you. And we're going to bring back samples from Mars which may contain something similar. Anyway, it's going to be quite difficult. So why are we interested in the oldest traces of life on Earth? Firstly, it's because they are the closest we can get to the origin of life. I'll show you why. We've lost the rock record. We don't know how life emerged. We don't know when life emerged. And this is the closest we can get to it. These traces, they're 3.5 billion years old, but they're already pretty evolved, which means that life emerged a lot earlier. They are also similar to what we think would be potential life forms on other planets, such as Mars, or maybe the icy satellites, Europa, Enceladus, around the giant planets. And also, for something really important is if and when we do manage to detect traces of life elsewhere, either in samples that are brought back from Mars or other planets, or detect life around exoplanets, which will be pretty difficult. This is super important because it tells us we think we know how life emerged on Earth, theoretically. We haven't been able to do it in the laboratory yet. It's a very simple process. It's chemistry that evolves into biology. It's so simple we don't know how to do it. But anyway, that's the idea. But if we do manage to find traces of life elsewhere, this supports the hypothesis that it's a pretty simple process. Anyway, a reasonable process. So I'm just going to show you a slide to explain what the constraints are about searching for the oldest traces of life on Earth. So this is a lovely sketch from the NASA National Astrobiology Institute, showing the evolution of the Earth and evolution of life, from the formation of the Earth in a violent fashion to molecules coming together, cells coming together, evolution of the cells, differentiation, populating the seas, populating the land, up to the telescopes of today. It's a lovely sketch. But the important thing is, well, we don't know when life emerged, but we think it probably emerged between 4.3 and 4.2 billion years ago. That's when we think we have indications that the planet was habitable. What are the oldest traces of life? The oldest traces, really well-accepted traces of life, apart from my stuff, of course, is about 3.5 billion years old. There may be some traces in rocks that are slightly older at 3.7 billion years old. These are the oldest well-preserved sediments on Earth. Problem is, we've lost 1 billion years of history of the Earth due to impacts, tectonic processes, etc. We've lost it. It doesn't exist, which is also why we're interested in looking for life elsewhere, perhaps on Mars. So that's the constraint. That's why we can't go further back in time. Now, about setting the scene and the violent start to the Earth, because the evolution of life on Earth is contingent on the evolution, the geological evolution of the planet, because the planet has changed a lot as well. To begin with, okay, planet-forming pebbles or planetesimals or whatever, a really violent planet with magma oceans. The planet's starting to calm down. First atmosphere, first volatiles degassed from the mantle. Bang! An impact with the moon, with a planet the size of Mars. And the whole process starts all over again. And it just carries on. I mean, even today, we're still getting impacts, but at a slower rate. So the early Earth was quite violent and very, yes, interesting, adventurous. Nevertheless, as of about 4.2 billion years ago, our planet had water, had oceans. And in fact, our planet was like an ocean Earth, an ocean planet. There were basically no continents as we see today. It was just water everywhere. And in fact, the only continents that we had were, they were submerged. There was something like the Iceland plateau, but mostly underwater with the peaks of the volcanoes standing up. And this portion of the upper crust, the top of these, what we call proto-continents, that's all that's left. Everything else has been destroyed. All the deep ocean crust has been destroyed. So this is what we're working with. And I'm just giving you here a summary of what the general environmental conditions were on the early Earth compared to today. These we infer, we can measure from the ancient rocks, or we can infer them from proxies. Today, the average ocean temperature is about 4 degrees centigrade. Well, on the early Earth, at the rock-water interface, and that's very, all the ocean, the seas, they were shallow seas, lagoon-like things. We're talking about 50 to 70 degrees. That's even hotter than my bath water. So it's rather hot, but the bugs loved it. The pH, we have a carbon dioxide atmosphere, so the pH is rather acidic, too acidic compared to the ocean today. Atmosphere, almost no oxygen. And because there's no oxygen, there's no ozone layer, UV radiation coming zap, 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 straight down on the surface of the Earth. It's been calculated by Charlie Cockell and his colleagues using a kind of DNA weighting system, that there's something like between 54 watts per meter squared of radiation reaching the surface of the Earth 4 billion years ago compared to 1 watt today, but generally going up to 1,000 watts. So, so very, very highly radiative environment. And then just keep in mind, we're on a very hot Earth, very active, volcanoes, 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 hydrothermal activity all over the place, and still impacts. So that was the Earth. This was an Earth which we would consider today extreme, but our view is very limited because our Earth today is extreme. This place is the norm. What we're living on today is totally extreme, and we are the extremophiles. So, anyways, this is an artist's impression of what the early Earth looked like. We have a closer moon. The Earth was turning much faster. We've lots of hydrothermal volcanic activity, lots of storms, etc. As I said, carbon dioxide atmosphere. So, very, very different environment. But this is the environment in which life emerged and in which early life evolved. I'm going to talk to you a little bit now about what we find. I mentioned earlier that there's quite a wide diversity of life already by 3.5 billion years. If we look at the life in terms of going from the most primitive to the most evolved, and I'm talking about anoxygenic life, life without oxygen, the most primitive organisms are chemolithotrophs. They obtain their energy from oxidation of inorganic substances. Slightly more effective are the chemoorganotrophs, who obtain their energy from oxidation of carbon matter. And they like nutrient-rich environments. And the phototrophs that came later, evolved later, they obtain their energy from sunlight. And sunlight is everywhere available. So in terms of efficiency, metabolic efficiency, size, energy available, it goes from the most primitive to the most evolved, always without oxygen. So these are some examples, and I'll talk about each of these. I'm going to start off with the most primitive, because this is what I'm still working on. I was working on these organisms 22 years ago. I'm still working on them using state-of-the-art technology because it's so difficult. But this is what I think we might be getting back from Mars. So these chemolithotrophs, I call them the rock lovers because they oxidize the inorganic substrates. They leach elements such as nickel and iron. And these are some of the fossils or the organisms that we find. I'm showing you here examples of chemolithotrophic organisms that are around today. They're very small. They're less than a micron in size. And they eat rocks, literally. You can see here, this is a fluorescence microscopy image, and thanks to Guillaume, who's here in the room. These are volcanic particles, and what is fluorescing are the colonies of these organisms that are busy eating them. And they eat them very quickly. So I'm going to take you, as I said, I'm taking you on a voyage in time and in space. We're now going to go to Australia, to the northwest part of Australia, to the Pilbara region, to rocks that are about 3.5 billion years old. And the environment I'm going to show you, it's a coastal environment, a fossilized coastal environment, something similar to the Bay of Mont Saint-Michel here. Just forget about the trees, etc. They didn't exist, of course, in those days, but this is the kind of environment that we're looking at. So if you take a spade and you cut through these sands, these sediments, you see some structures, sort of intercrossing structures like this. And this is typical for tidal environments, this kind of structure. This is exactly what we find, same thing in rocks that are 3.5 billion years ago that are now found in Australia. And in these rocks are the fossils that I'm going to show you now. So what do we do with these rocks? Well, we take a sample, we make a thin slice of it, and here in the detail, you have an image of a thin section. It's 30 microns thick of this rock, And the spots that you see, these are volcanic particles. The scale bar there is 200 microns. Now, volcanic particles, this is an image here of volcanic sands. Volcanic sands are different to the normal white beaches that you see on the Earth today. These are sands that are highly enriched in the elements, the transition elements that the early microbes loved. So this is what we're looking at. Now, if you have a look at some of these particles, you can see that the edges are dark. They're dark because they are coated with carbon. This is a Raman map done by my colleague Frédéric Fouché of one of these particles. The green is carbon. Why is there carbon there? Oh, and by the way, it's not just any old carbon. This particular shape of the Raman spectrum tells us it's very, very ancient carbon. It's consistent with the age of the rock, which is important. So we study these particles further. This is our thin section observed with the electron microscope. Our volcanic particle here is light grey, and you can see the sort of tunnel things going from the edge to the inside. The mid-grey is silica, because the early oceans were enriched in silica to such an extent that everything was lithified, silicified within days. I mean, really, really fast. I think perhaps it's going to be easier if yes, it's easy if I can do this. So what we see here are these tunnels, and these tunnels are filled with a kind of filmy substance here, which we call EPS. It's all silicified. And then at the edges of the particles, we see areas with beads, very small beads, less than a micron in size. They're full of carbon. We can see the carbon map here. And these beads consist of these features. Now, these are what I have interpreted as fossilized chemolithotrophic organisms. At the top here, you can see what remains of the volcanic particles. But this is like a carpet of beads. But you can see cell division coating with film, which is extracellular polymeric substances that the microbes secrete. But the detail is absolutely exquisite. Remember, we're looking at organisms that lived in this environment 3.5 billion years ago. Can you see the cell division here? Beautiful. Here, the cells are just starting to move apart. And in this organism, it divided, and then one part died, and the other kept living. This part where it's gone all flat, the organism lysed. You've got living life and death in one image of a rock that's 3.5 billion years ago old. So absolutely exquisite. But there are caveats. And the caveats are that there are a lot of minerals that look like fossil organisms or organisms. I've put up here some coccoidal microorganisms. And here, as for comparison, I've put some spheres of hydrothermal silica. They're just round spheres. And also, we find extraterrestrial carbonaceous spheres in meteorites. They have the same size, they're just round objects. How can we tell the difference between something that's not biological and something that was biological but has been fossilized? That's the real difficulty that we're facing. And not just that. If we manage to say, identify that something really is biological and it is a fossil, the question is, did it form at the same time as the rock, or did it come in later? And this is important. Here at the bottom, I'm showing you a rock that is even older than the one that I mentioned earlier. It's nearly 3.8 billion years old. It comes from Greenland. But we find fossilized microorganisms. These are fossilized cyanobacteria that infiltrated the rock since the end of the last, since about 8,000 years ago, because these are organisms that like living in rocks. They find they're called endolithic organisms. So we've got to be careful about that. And this is really important we have to demonstrate the biogenicity, and the only way to do it is by using a battery of techniques to detect different kinds of characteristics, the morphology, the composition of the remnant organic matter, the carbon isotope signature, the organo-biogeochemical signature, the transition elements that are still associated with the fossils, And this is what my PhD student, Laura Claudery, is helping me with at the moment. Plus, this is, I'm doing some state-of-the-art work with time of flight, secondary ion mass spectrometry. Then, okay, as I said, we're trying to, let's say we managed to determine that these are biological features. Did they form at the same time? Well, I have an image here of a microbe dividing. It's still half embedded in the quartz crystal. That means that it was there before the quartz formed, and the quartz formed very, very rapidly. And we can see other examples here. And this is what Laura Claudery is doing as well by analyzing the organic matter associated with these volcanic particles. And what I'm doing with the Toff-Sims analysis of the organic matter. So just to underline the difficulties of what we're dealing with. Now, we're going up a level in terms of energy, of metabolic efficiency, evolution, etc. We're going to go to the chemoorganotrophs. I call them the cannibals because they basically live off the remains of these chemolithotrophic organisms. So if you have your volcanic particle with the chemolithotrophic organisms around it, once they've got all of that energy, they just die. And then they're colonized by the chemoorganotrophs, but only in areas where there's high nutrient flow, and that means very close to hydrothermal environments. And this is work that I've done also with Kathy Campbell, who was a fellow here. So what we're seeing here in this rock, it's a layered rock. It has the same layered sediments as we saw before, but they are totally silicified. They're black because they're 99.9% silica. They are completely silicified. But that's because they're formed around hydrothermal vents. These are the fossil hydrothermal vents. And this is... and it's in these environments, in these really what we call black cherts, that we find the chemoorganotrophs, because they want more energy. They want the small molecules that are coming out from the hydrothermal vents. They need extra energy. And the rocks, this is what the rocks look like in thin section. You just see spots. But the spots are very strange in shape. I mean, they've got no regular shapes. They're all sort of spiky, stellate. They formed in situ in a kind of gel, silica gel, dusty, volcanic dust silica gel. And former PhD student Kieran Hickman-Lewis did some very good work looking for concentrations of these transition metals associated with these organisms to document some kind of biogenicity associated with the colonies. He's now at the Natural History Museum in London, and he's working with the Mars 2020 mission and the Perseverance rover. So, next step up, we're going to the phototrophs now. We get the energy from sunlight. So, phototrophs, they need sunlight. So they live where there's sunlight. If you have swimming pools or basins and you get sort of green slime around it, the green slime, these are phototrophic organisms. And I'm going to show you examples from the coast, an ancient coast. Again, imagine the Bay of Bournemouth. Again, if you take a slice through the Bay of Bournemouth and you look at it with the microscope this time, you can see these layers. These are layers of phototrophic microbial mats. And this is what we see also in the ancient rock record. This is a slightly younger rock from Barberton in South Africa. South Africa is my birthplace. We can see layers of phototrophic mats here, filamentous layers. We can even see that they've been overturned by flow. And this is preserved. It's nearly 3.5 billion years old. And you can still see these kinds of details. It's absolutely incredible. And this is work that I've done with Barbara Cavalazzi, another Studium fellow. I'm not going to talk much about this. All this is supposed to do is just make you think, oh my gosh, and go, wow. It's just to say we use up to synchrotron techniques to try to study these features to understand their biogenicity, etc. And we can get a lot of information from them. Now, I'm going to finish off with a trip to Mars. So, tighten your seatbelts, and we are off to Mars. Now, this is the habitability of Mars today compared with the habitability of the Earth. Obviously, Mars is a cold, dry desert today with almost no possibility of having life on the surface. But 4 billion years ago, there was water on the planet. There's a colleague of mine, Dave Desmarais, made a very nice sketch to illustrate the evolution of Mars from when it was habitable, when life could potentially have been on the planet, to today. This is 4 billion years ago on the left, today on the right. And we see the evolution of the planet. There's water to begin with, but the planet's a lot smaller. For various reasons, it lost its water. It's become a dry desert, and the little microbes are thanks to Frédéric Fouché. His mother's an artist, so he's got quite some artistic talent. So the microbes that might have been alive 4 billion years ago are certainly dead and fossilized today. However, there's still possibility of some life in the subsurface of Mars today, but we'd have to drill to find it. Now, I want to talk to you about our European Russian program, ExoMars, the ExoMars mission. The ExoMars mission was born here in Orléans. Why? Because the ESA team that discussed an astrobiology mission to Mars at the end of the 1990s was headed by André Brack, my predecessor, and I was in that team, which is why I'm here today. So, and this is my contribution to it. So we've been working with this mission since 1997. We are now 2022. We were supposed to have a launch in September. Everything was ready for shipments to Baikonur in the first weeks of Mars, but unfortunately, at the end of February, there was a little invasion of a certain country, which meant that our mission is going kaput. 25 years of work. Will I see the mission? I hope so, but not rapidly. Anyway, sorry, that's a sideline. So I promised Athena I would be talking about TGO. Here you are, Athena. The mission consists, actually it's two missions. There's an orbit, oops, sorry, how do I go back? No, that's not what I want. There we are. There's an orbiter, the trace gas orbiter, which is working very, very well. There was a demonstration lander, Schiaparelli, that went splat, unfortunately. And then the Rosalind Franklin rover, which is a masterpiece of, I was about to say a masterpiece, it is a masterpiece of engineering, but it's pretty ugly. Yes, I can show it to you better here. In fact, the engineers at ESA call it the bathtub. They complain, this instrument, the rover, was made in Italy, where you have Ferraris, where you have Bugattis, you have the most beautiful aesthetic things, and they constructed this bathtub. Anyway, it works very, very well. In fact, the rover, it's an ensemble of the geologist in the field. I'm a geologist, I do field geology with the eyes, etc., some instrumentation, and also the possibility of taking samples in the deep subsurface, because this is something that the NASA missions don't have. We have a drill that goes down to 2 meters, and analyzing the samples with the instruments inside. I won't go into too much detail about this. I just want to talk to you about the microscope. That's my instrument. I proposed a microscope for the mission in 2003, or was it 2004? It was accepted. The PI of the microscope is Jean-Luc Chaussy in Switzerland. He's a physicist. This microscope, it's had to be housed on the drill because it used to be on an arm, but Europe didn't have the money, so the arm was amputated. Where do you put the microscope then? Well, they're very ingenious. It's housed on the drill. It can look at outcrops. It can look at the samples coming up from that are sampled. But although the microscope is very powerful, the kinds of life forms that we are expecting on Mars are too small. They're less than a micron in size. We won't be able to see them. We may be able to see something like this black rock with spots in it, which may be indicative of colonies inside. But, as I mentioned, we know that these fossils still contain traces of carbon, and it's the carbon that ExoMars will be measuring. the remains of the carbon. We're not expecting things like amino acids, nucleotides, etc. We're expecting more degraded molecules, perhaps molecules that can be traced back to the original lipids, for instance, the stearanes, the hopanes, or something so degraded like thiophene, which is, it's biogenic, but it could also be abiogenic. So I've tried to show you a little bit to take you on a trip to another planet, show you why this early planet is very interesting. It's interesting for understanding the origins of life on Earth. It was especially the early evolution of life on Earth, why we're using these examples as analogues of Martian life, but the very best, of course. Is a geologist on Mars. Now, in 1998, I went to work at NASA, at the Johnson Space Center in Houston. I was convinced I would be the first geologist on Mars. I'm still waiting. So I'll finish there. Thank you very much.